is the total energy of the system, right? So we had U of the system plus what other components could we consider besides the system? Yep, the surroundings. And if we add these two things together, what are we getting? Delta U of what? Yep, universe. So everything in the universe. Now, remember, this is like the total energy of the system, right? What did we say if we apply the first law to this rule? What's going to change in here? Yeah. Right, because what's the first law say? Right, energy can't be created or destroyed. That means the change in the internal energy of the universe has to be equal to 0. And we arrived at this expression, delta U system is equal to negative delta U surroundings, right? Okay, which of these is easier to measure, do you think? Why? Yep. The other thing is if you wanted to measure the surroundings, like what's the definition of the system? Like what does this delta U of the system mean? Or what is a system? Yeah, the part that's being observed, the part of the universe that we want to observe. This is everything else, right? It's hard to measure everything else in the universe as we go along. So, however, it is difficult to measure delta U surroundings. So a more useful way to write this to write the first law is to only consider delta U of the system. So delta U of the system, we have to look at the energy coming and leaving from the system. There are two ways that this can happen. Does anybody know the two ways energy can be transferred in and out of a system? Yeah. Yep. So heat, any other things. There's one other one. Pressure, yeah, it's related to pressures or work. So joules going in, joules going out. So the internal energy of the system is defined by the heat transfer and the work being done to or by the system. So we said Q, what's Q again? Yep, heat transfer. And what's W? Yeah, work done to/by system. Okay, so now what we're going to do, yeah.
So the change in energy in the system would be usability?
Yep.
Okay.
And the thing is this is a state function, whereas Q and W are not state functions. They're actually path-dependent functions. It's kind of weird. You can slap two path-dependent functions and get a state function. What's a state function again? Like, what's the purpose of it? Why is it beneficial to have a state function? Right, you only care about the initial and the final state, so you don't have to sit there and continually watch the system. You just have to look at the final and the initial states.
If you have a question about this, like when teaching from the work on a test, are we going to give them the teaching and the work, or are we going to have to solve for it?
You're going to have to solve for it, and we're going to do some of those problems later today.
Okay.
Okay.
So when we get the equation for that thing, or should we not?
You should know it based upon the units. I wouldn't say memorize it. Okay? All right, so let's consider, we're going to consider our two properties here, Q and we have W. We're going to keep track of their sign. So we could have positive Q, negative Q, and have positive work, negative work. And we want to look at the meaning behind it. So we want to consider if energy is entering or leaving the system, and what type of process is that. So, Q is positive. What does that mean? Is this an exo or an endothermic process? What's happening to the total energy of the system? Is it going to increase if this is positive or decrease if this is positive? It's going to increase, right? So, energy is entering the system. What type of process do you have energy entering the system through heat transfers? Yep, it's endothermic. We got endothermic. And if it's negative, what's that mean? Yep, exothermic. Energy is being released. Now let's consider a positive and a negative work. We have to figure out if work is being done to or by the system. Okay, if work is positive, what's happening to the internal energy of the system? Is it increasing or decreasing based upon this equation? It's increasing. Does that mean work is done to the system or by the system? Yep, it's done to, because energy has to enter the system. So work done to system. And what does the work on the system? If we want to keep with this technical thermodynamics linguistics. Work is done to the system by what? Yeah. By the surroundings. So now what does a negative work mean?
The system didn't work to the surroundings.
Yeah. Work done by system on surroundings. So it's important to keep in mind, like, when is energy entering and leaving the system? Okay? Now let's ask a question. When do we have an energy depleting process? So let's hop back. We have first law of thermo states what? Delta U is equal to? What's it equal to? We just talked about it. Sierra, what do you think? That is true, but I want to utilize these things. I want to talk about heat and work. Yeah. So we got those two things. All right, now let's consider. We have an energy depleting process. What does that mean about the value of delta U? Greater than or less than 0? Less than 0, because it has to be a negative value, right? Okay, under what conditions are we going to have a negative delta U? Yeah. Yep, that's one instance. Q is negative. And work is negative. Is that the only situation? No, give me another one. let's say Q is negative, what about the sign of delta or W? So what conditions does this have to be true? Or delta U to be less than 0? Yep, the absolute value or the magnitude of Q has to be greater than the absolute value of W. Now, we know what has to be true if we have the opposite, a positive Q, we have an endothermic process, and then our system's doing work. What has to be true in that case? Yep. Ooh, that's meant to be a straight line to show magnitude or absolute value. Makes sense, right? So you want to consider those things later on when we're looking at what happens to the energy of the system. Is it going to increase or is it going to decrease? Okay? Any questions about this yet?